Hello everyone, my name is Carson Beekadam, and today I'll be presenting my Lab 2 project for Physics 2211 on projectile motion. For this experiment, we used a hacky sack with a mass of about 0.055 kilograms. We threw the sack in front of a neutral background and recorded the motion with video. Then tracker software analyzed the motion. The coordinate system was set up so that the x-axis was along the back wall of the whiteboard, with the origin at the launch point. Assume there was no camera motion and use a meter stick for calibration. The ball was launched with a roughly constant throwing force, so we can assume there's no additional application of horizontal force in the projectile. Here is a sample of the data collected from the tracker, which included time, x position, and y position. These measurements were compared against predictions of computational models. Some possible sources of error included incorrect calibration, tracking clicks, or the frame rate being a little bit too low for smooth tracking, as there was a limit for about 50 FPS on the tracker software clicking, as opposed to maybe a max value of 60 FPS or 7 FPS. Computational models. Two different models were tested. The first was gravity only, where the net force was simply downward, equal to the negative mass times gravity. The second model included both gravity and a drag force, with a drag coefficient of 0.06, equaling b. The drag force was modeled as a negative b times velocity squared in the direction of velocity, um, or the unit vector. Um, both models were implemented in GlowScript v Python with visualizations that showed arrows for velocity, drag, and gravity. Movement also only pertains in the x, y planes, so there's no need to represent a third dimension, or z. In terms of acquired trajectories, the acquired trajectory for the hacky sack in this experiment was compiled using Tracker app. As you can see, the tracking of the object begins with the object ceasing to have fnet in the horizontal direction or when it leaves the hand. And the net change in position in the y-hat direction is negative, as the object is no longer tracked when its position is below the chosen x-axis. In terms of results, you can see the trajectories overlaid on the slide. The experimental trajectory is compared with the gravity-only model and the gravity plus drag model. The gravity-only model predicted that the ball would travel almost 4 meters, landing 1.2 meters below the launch point. The drag model also predicted a shorter distance, less than 2 meters, and a landing of about 0.9 meters below the launch. The B-value had only a small effect overall, but the drag model clearly fit the experimental data more than the gravity-only model in this case. And here are results on the velocity graphs. We didn't observe any terminal velocity because the motion was way too short to do so, but we can see that drag slowed down the motion compared to the gravity-only model, causing it to fall short. According to the gravitational models, there should have been little y-position dispersion over the same time interval, and the time would take much longer to hit the ground, which is correct in this case. But what does this mean? Terminal velocity occurs when drag balances out gravity. In this experiment, the ball never dropped long enough to reach that point. So if the object had been thrown straight up, then without drag, the motion would be symmetric on the way up and down. But with drag, the ball will return sooner and rise more slowly. There were significant experimental errors observed in the imperfect fit of the b equals 0.06 drag model, as the trajectory appears much lower for the observed trajectory y-hat positions than on GlowScript. Additionally, the path of the ball appeared to form a roughly symmetric form, as opposed to a slower rise and a quicker drop, as exemplified through drag forces. And then to conclude, the models predicted projectile motion well, with the drag model giving a closer match to the experiment. However, considering the relatively low coefficient of drag, or 0.06, the small drag effect the density of the atmosphere did have on the object almost halved potential trajectory distance. Limitations also included the short recording time, small tracking errors, and the relatively low frame rate, which made it difficult to precisely follow the hacky sack. Additionally, future improvements could be made, including testing for terminal velocity with a longer drop, and additionally could be adjusted straight up and down to adjust the overall vertical velocity without accounting for horizontal velocity, just to make sure that the the experiment was more accurate. And in this experiment, the time interval was too short to accurately determine the drag coefficient, which is another factor that we would adjust. And that's it. Thank you for watching.